Welcome to Chapter 3. This is the short section on forces and further equilibrium ideas, but the main thing is it's all about rotation. So we already have pushes, we have pulls, there are standard forces, we can draw those with vector arrows, we can do this as well. There is nothing in the chapter that you're expected to have covered before. Some of you may have done moments, so if you have, that will help a little bit, but it's mainly about stability and descriptions. Okay, so the key thing is you may have done this, but you may not have. What we're going to do is just do the basics today, quite factual, so just get you into it, and then really thinking about the idea of stability, because that's what matters for us the most. So, the key idea behind this is what we actually mean by equilibrium. If we had something that was sat on a surface and we were to just push on that, well, that would be great. It would move along. Why? Because there is an unbalanced force, and you well know that if there is some sort of resultant force, that causes objects, in this case my box, my mass, to accelerate. So a basic version of the Newton's laws equations means that if you've got some sort of force, you're going to get some sort of acceleration. It can be moving, but it's about the change. And if we have this force here, we have this idea that, okay, it's going to move, but it won't usually accelerate if you're trying to slide a box across the floor, because you have friction in the opposite direction. So that friction is usually about the same as the force, so they tend to slide at a nice steady rate when we're moving things across the floor. However, if we do this, it's still not in equilibrium. The forces, okay, the forces will add up to, so the sum of the forces will still equal 0. However, fairly obviously, if you try shoving the top of something and the bottom is jammed, or is being slowed by friction, that whole thing is going to actually tip over and move away over into this direction. So the whole thing will tip over. And because of that, we must have something a bit more going on with equilibrium. And what it is the idea of moments. Okay, so the moments are also forces, kind of. They're also going to have to add up to nothing, because we don't want this to twist. We don't want it to change its acceleration, or change its motion rather. Example, most obvious one to me, is if you're thinking of a rocket and you have some sort of landers on the side of, jets on the side of a lander that's coming down, and we have the planet's surface below you, and you have your two jets like thus. Fine if we are pushing upwards with that, so we've got force due to the gas coming out the bottom. It might go nice and steadily down towards the surface, but if one of them cuts out, that force is no longer there, and what will happen is that this will rotate. And how quickly this rotates depends on two things. It will depend on this force here, but also how far it is to the middle of the object, because it will spin about the middle points. The midpoint of this has a very special name, centre of mass, because it's the centre of the mass. So if they think of that centre of mass there, if the force is off to one side, it will twist. And so it's this that we're considering in this chapter. Now, when we go inside, the actual definition of it is very similar to the work done equation that we will see later, and we'll see much more, but do not get confused. What actually matters is if we have some pivot or fulcrum, usually indicated by a triangle, kind of works with seesaws, but it also works as the axle of a wheel, for example. So if you want to call it a fulcrum, please do, but pivot is fine, maybe even the axle, depending what the situation is. But it's this force twisting the object around, so it's that push there that matters, not the push forwards or backwards. And although this looks like a linear force, it's not. It's actually rotating around with it. So what we're talking about here is a force that's at right angles to a distance. Okay, work done is when you're pushing something along a distance. So here we have a rotational force. That rotational force combined with the distance gives us this thing called the moment. Okay, so definitions wise, what we've got is the moment, or any moment which doesn't have a symbol, so we actually have to use the word moment, is the force, the product of the force, so multiplied by the force and the distance perpendicular to that force from the pivot. So from the pivot itself. Now the force hopefully is at right angles, but often strangely enough they're not, and so we get this idea of vectors in here. This force, instead of turning it around, is pulling outwards as well as turning it around. So the idea is we've got a perpendicular force, but we've also got a force that's kind of wasted because it's trying to pull out on the axis. So we don't want that. We want to think about this right angle bit. Me personally, I tend to think of which is the distance and which direction is that distance to give it a right angle. So I will change the length, the distance from the pivot, into a shorter version. And if we look at that, it's a right angle triangle, angle there, it's adjacent to the angle, so that's going to be d cos theta. So if we take the equation above, I'll just put mom instead of moments. That's going to equal still the force, however big that force is, which is perpendicular to d cos theta. Whereas if we are talking about the change in the force, so we could change the force into its components instead, again, if we look at that, it's still adjacent to the angle, and so our force becomes F cos theta. And if we put that in, well, our moment F cos theta times by d, it still ends up as the same equation. Okay, so it's still force times distance from the pivot, perpendicular distance. You just might need to put the cos in to get yourself that right angle. So it's the right angle that's important. So, quick check, the units are newtons and meters, they're your standard. You can use more convenient ones sometimes when we get onto balancing seesaws and things, but try and get it into newtons and meters. Do not shorten that to joules, okay? It doesn't. So, if you're talking about newtons and meters moved, so that will be work done, then it does give you joules of energy, but not here. Okay, so Newton meters is right, just stick with that and it's so much easier. So sometimes we will have more than one force doing the job. Again, I'm going to just pick up one thing because I've put D here again. In the data sheet, I think it's very confusing. It says moment equals force times x. But x to me is extension, it's distance moved in the right direction. Some exam boards will use s, okay, which I've given it there as well. But I think d makes you think about it. It is distance, but it's perpendicular distance. Exclamation mark, exclamation mark. By all means, get into the habit of using FD and write it in your data book if you want. If we get down to here, the equation for torque actually does say FD, but they are using D in a completely different way and they don't use it in the proper way. So I would suggest you don't do that. By example here, for example, you're playing with an aeroplane, a toy aeroplane, whatever it is. If it's flying through the air and you change one wing, well, the other wing changes as well, and both of them are producing that force that rotates the plane around the central axis. In this case, it is an axis, an axle through the middle, and it's going to rotate around that. If we do that, we end up with the torque. So they call it that because they want to make it different from moments, but it actually is just moments. As long as they're both changing it in the same direction, whichever direction, clockwise or anti-clockwise. But torque equals FD plus the other FD, okay, so distance from pivot, right angles there, and so you end up with 2FD, which actually gives you force times diameter. Okay, because most of the questions will actually be around a circle. Okay, for example, a steering wheel where you hold your two hands both sides of the wheel and both hands do the same thing. They're both turning it in the same direction. So that's why in the data book you get a D in the equation. And if you have it at a bit of an angle, again, you can go through exactly the same maths before, but you'll find that you'll get exactly the same answer. So, torque is F times diameter multiplied by cos theta. Okay, so those are the main ideas. However, the bit that matters is breaking down that equation. You will get a bigger twisting effect if the distance is bigger or if the force is bigger. Or thinking of it in a different way, if you have the idea of a door being pushed open, like with our starting picture, you'll find that depending where you push, you would need different size forces to open it up. So if we have this is our pivot, these are our hinges here, okay? If I had something that is twice as far, then because that is 2D to the pivot, I need a certain size force. But if I'm only going half as far to a distance D, then I will need 2 times the force, because 2FD will equal 2FD. And the size of force needed to rotate, the rotational effect, is going to depend on the friction of the joint. If you've got a rusty door or rusty hinges on your door, it's going to be much harder. You're going to have to push much harder. So again, to do the turn, however much you need for the turn, that moment, how much force you need depends on how far away from the pivot you are. Okay, it's a really, really useful idea, and there's a bit of practice in the back. We don't actually need to add any more really to this section, because that is pretty much all the mathematics of this. Okay, so what I want you to do is go into the back of your book, and before we build up to kind of descriptive stuff that's coming up, I want you to practice the questions in the back. Fairly straightforward. We'll do some in the lessons, but practice makes perfect with all of these. You'll find, as usual, it's the diagram at the beginning that's awkward. Okay, but if you keep going back to force times perpendicular distance, underline, that's your definition. If you use that definition, you can't go wrong. Okay, so you just need to change any forces and distances that are diagonal into a right angle. Okay, thanks very much, guys.